Hello AP Physics students. This lesson is going to introduce you to vectors, vector addition, and resolution. Please have the two handouts in front of you that you got in class. One, as this slide says, is the notes, vector addition, resolution. It's a single page. And the other, a bunch of stable pages called notes, vectors, and two-dimensional kinematics problems. Now that you have both of those in front of you, we'll start with vector addition. When we say addition, we're not necessarily just numerically adding the magnitudes of the vectors. This is a method of combining the vectors and seeing the overall result. Regardless of how we do it, we still call it an addition. And I'm going to introduce you to the tail-to-head method, which is the simplest way of combining vectors. There are other methods that exist, but this one I find is a great routine to get into that always gets you a correct answer. It's a three-step process. First, to draw the first vector with proper orientation, which means draw it east or north or up or down according to the directions given. Step 2, shift the second vector until its tail is at the head of the first. Continue in this manner with any remaining vectors, and that process will become clearer as we go through our first couple problems. Step 3, draw the resultant vector from the tail of the first to the head of the last. Here we define resultant as the single vector that gets the same results as the original combination of vectors. So we'll try a real simple problem. It's right there in your notes page. Let's say you walk 3 meters east and then 4 meters north. What is your overall displacement? To start us off, we have a compass rose here drawn with north pointing to the top of the page, south to the bottom, east to the right, and west to the left. That's a real standard way of doing it. And we'll start here with step 1, draw the first vector with proper orientation. So the first vector here is the 3 meters east, and east to the right of the page, so I've drawn it 3 meters east. I've drawn the second vector here as well, just so you can see if we draw it this way, it's not really useful. So we go on to the second step, where now we draw that first vector again, but now we shift the second vector so its tail, this end, is touching the head of the first vector. So this is our tail-to-head connection. So it's like a person walked here 3 meters east, turned, and then walked 4 meters north. And so the tail of the second vector is touching the head of the first. If there are more vectors, 3 or 4 or 5 vectors, we just continue in this manner. So we go first vector, tail-to-head second vector, tail-to-head third vector, and so on and so forth for any remaining vectors. The third step, as highlighted above, is to draw the resultant vector. Now here I draw it in a different color, which I strongly advise you to do, a different color, pen versus pen, pen versus pencil, or make it a bolder line or a dashed line. Maybe you want to pause the video now and get another color to use if you want to draw your resultant. According to step 3, we're going to draw the resultant from the tail of the first towards the head of the last, and that should make sense because if a person were walking this way 3 meters east and then 4 meters north, and then a different person were to start here at the same starting point, walk along this blue vector, they should end up at the same spot. That's why we call it the resultant vector. It gets the same results as the original combination of vectors. So we draw it from the tail of the first towards the head of the last because that is the direction a person would walk to go along this total displacement, and here we call this delta x total for total displacement. From here on out, it's a very simple process to get the magnitude and direction for this displacement. The angle, since this is a vector, we need the angle here, will be the angle near the starting point, because the person starting here would turn themselves through this angle to walk along the blue vector, which is considered to be like the shortcut distance. Here we're just going to use trig, and I like to use the inverse tangent function, although certainly inverse sine or inverse cosine will get you similar results. I like to use inverse tangent because we already have the two sides of the triangle, where here the 4 meters is opposite to theta and 3 meters is adjacent. So that would be inverse tangent of opposite over adjacent, or 4 meters over 3 meters, and you type that in your calculator, and you get an angle of 53 degrees. This is a 2 sig fig problem, since each of these magnitudes has 2 sig figs, your angle ultimately has 2 sig figs. And then a simple Pythagorean theorem will get you the magnitude of the resultant, although you can just recognize this as a 3, 4, 5 right triangle, so you already know the total displacement and magnitude will be 5 meters. As we put it all together as an answer of 5 meters at 53 degrees north of east. Now this person clearly walked east and north, but we can't say this person walked directly northeast because northeast is exactly in between north and east. There's a 90-degree angle between north and east, and so exactly between will be a 45-degree angle. So we reserve northeast, northwest, southeast, southeast for a 45-degree angle. That's clearly not here. We don't have an isosceles right triangle, as that's why we had to find the angle for the direction in the answer for the vector. Why is it 50 degrees north of east? Well, imagine a person standing here and they're facing directly east. To walk along the blue path, they would turn themselves from east towards north 53 degrees. They'd face east and turn 53 degrees away from east in the north direction. So we call that 53 degrees north of east. And this forms the whole magnitude and direction for the answer.